சரி. டக்குன்னு பார்த்துக்கோ. அவர் எப்பவுமே சரியா அவரை அட்மிட் பண்ணு. இப்ப பண்ண முடியாதா? கோபி வந்தார். உனக்கு போட்டு. இவரு வரல பாரு இவரு. சரி கோபி சார். கோபி சார் பாருங்க. கோபி சார் நான் பண்ணட்டுமா? கட் பண்ணிட்டு கோபி வந்துட்டாருங்களா? சரி தேங்க்ஸ் சார். போட்டுருங்க சார் போட்டுருங்க. அதை மட்டும் எங்கன்னு சொல்லுங்க. இப்ப நான் எங்க போனோம் சார்? அது இப்ப எங்க போனோம்? அந்த இது மாத்துறது ஆப்ஷன். எஸ். ஓகே. அட்மிட் ஆல் இருக்கு. கோஹோஸ்ட் எப்படி சார் கொடுக்கணும்? அது ரமேஷ் ராஜகோபால் போஸ்ட் மீ அப்படின்னு இருக்கு. வேற என்ன இருக்கு? மேக் கோஹோஸ்ட் போட்டு இப்போ பாருங்க வந்துருச்சான்னு பாருங்க. எஸ் கொடுக்கோ. டு யூ வாண்ட் டு மேக் ரமேஷ் ராஜா கோஹோஸ்ட்? எஸ். Okay, fine. Good evening, Mohan. Good evening.
Sir, good evening, sir.
Nice to meet you. Yes, sir. Good evening. Very kind of you, Mohandas.
Thank you, sir.
Okay, sir. Good evening. Sir, good evening.
So please unmute your mic, sir. Unmute, sir.
Sir.
Hello.
Yes, sir. அந்த கிளிக் பண்ணா எங்க கேலரி? எஸ் சார். ஆமா. இப்போ 9 டாட்ஸ் இப்போ வந்து இருக்கு சார். இப்போ அதை கிளிக் பண்ணிட்டோம்னா இப்போ ஸ்பீக்கர் வியூ போயிடுமா? நோ அது ப்ராப்ளம். இப்போ எல்லாமே மியூட் ஆகி தான் இருக்காங்கல்ல. ஸோ ஜாயின்ட் ஆல். யார்? ஓகே. இப்போ சார் வந்து அவர் இது பண்ணிட்டோம்னா அவர் ஈ கேன் மேக் இதில். சரி, ஐ ஹாவ் டவுட் டாக்டர் செந்தாமரை. ஸ்பீக்கர் வியூ இருக்குல்ல, அதை கிளிக் பண்ணணுமா இப்போ? Speaker view are there. I need not do anything now. Now it's comfortable. So I can admit the speaker today and I can make him to right. Yeah, fine. That I can do, and then I will do that. Please. Yeah. I will ask him to join. Is it audible?
Yes, sir. Audible, sir. Audible, sir.
Kind of you. Good evening. Welcome, Sandhir sir. Good evening.
Good evening. Good evening.
Very nice to receive you.
So I'll join after five minutes. Huh?
Please, okay. Mute. You can mute your video.
Mohandas, am I audible?
Yes, sir. Yes, sir.
Audible, audible.
Okay, okay.
Yes, sir. More யார் பண்ணாங்கன்னு தெரியல. செந்தில். ஓகே, நான் மேக் கோஹோஸ்ட் போட்டுடுறேன் சாரை. மேக் கோஹோஸ்ட் தான் போட்டிருக்கேன் சார். போட்டுறேன் அவர் செந்தில் வேலன் சார். Gopinath sir. Gopi sir.
Yes, sir.
Sir, I think you can parallelly admit participants who are coming, sir.
Sir, one more thing. Actually, you are not made me as a co-host.
Oh, I'll do it now, sir. Yes, sir.
Okay, okay. Okay, I got it. Yes, yes.
Dr. Mohandas, have you got it, sir?
Yes, sir. I got it. I'm also co-host now.
Yes, sir. Professor Sandhir Velan, sir, have you got co-host, sir?
Sir has not yet joined actually. I think he joined, but he muted and
Maybe, yes, sir.
he'll come back. He told he'll come back within after 5 minutes.
Fine. Yes, sir.
Sir, Ramesh, sir.
Yes, sir. He is out.
We
Yes,
were
sir.
asking for admission now. I can admit, na?
Yes, sir. Yes, sir. Yes, sir.
Yes, yes, yes. The Sandhamari is totally out of scenario or what?
No, sir. Some electrical problem.
Good afternoon, sir.
Good afternoon, Sandhamari.
Yes, sir.
I think Kumaraswamy called us, huh? Okay.
Pardon, sir?
Kumaraswamy called, huh?
Yes, sir. Yes, sir.
Oh,
Welcome, welcome.
welcome, Kumaraswamy, sir. Yes, sir.
Thank you, sir.
Uh, Mohandas,
Tell me,
while introducing a chief guest, you better unmute your camera.
oh, switch off my camera.
Yeah, during the what he told Ramesh sir.
Okay, sir. I'll switch off my camera. No issue, sir.
If you come through some professional dress now, okay. Now you are come by t-shirt. That is why. We are a professional college people. That is why.
Okay. Let me
Huh?
switch off my camera.
Okay, okay.
Okay.
Thank you, Mohandas.
Okay, sir.
Ramesh sir.
Yes, sir. Audible, sir.
Okay, okay, okay. All set to go now. Any problem? Any issue? No.
No, sir. It is comfortable, sir. We are in the right track.
Okay.
Sir, we are in YouTube live relay. So that, yes, sir. Mohandas, sir.
Yes, sir. Tell me, sir.
Yeah. Can you take, yes, sir. Audio and video both comfortable now, sir? Yes, sir.
And I can switch on my camera, but Gopinath sir told me to switch off the camera since I'm wearing t-shirt. Is it okay for you?
Fine, sir. It's fine.
No, I'm wearing t-shirt. Gopinath sir is telling I should wear the formal dress. That's why I switch off my camera.
What, Ramesh sir? What I suggested correct now? What do you say?
It's comfortable, sir. Yes, sir.
Yes, yes, yes.
It's comfortable. Yes, sir. Mohandas, sir, it's comfortable. Yeah.
Let me switch on my camera. You just suggest me whether I have to continue or if you want me to switch off my camera, I will switch off.
It's comfortable, sir. It's very comfortable. Yeah. Thank you.
Okay.
Okay, okay. Okay, Mohandas. It is
Okay,
my
sir.
main coordinator opinion. Based on main coordinator opinion, you can act. No
Okay.
problem.
Okay.
And now he is looking smart today.
Yeah, based on the request and not a request, order from the coordinator, Dr. Ramesh sir. I have done the shaving.
Okay, okay, good, good, good. Good, good. I think Sar has left, no? Senthil Valan sir, I think left.
He told me he'll come back within 5 minutes.
Okay, okay, okay.
I kindly request Professor Gopinath to permit the participants while
Yes, sir,
joining.
yes, sir.
Yes, sir.
Yes, sir.
Please take care.
Okay.
And I will connect with Senthil Valan sir, and I will ask his. I will ask
Yeah,
his readiness.
you proceed with that process. I'll admit the people who are asking.
Yeah, fine, sir. Fine. Thank you. Thank you. Yeah. Audio? Audio இல்லையா? நீங்க எஸ்வின்னு போட்டிருக்குமே அதானே உங்களோடது? செந்தில் வேலன் ஃபுல்லா இருக்குமா? ஓ, செந்தில்னு இருக்கு தனியா. ஓகே.
Yes, sir, he has joined actually. Senthil Velan sir has joined.
செந்தில் வேலன், எஸ் எஸ் சார். செந்தில் வேலன் ஃபுல்லா இருக்கு. கோஹோஸ்ட் போட்டிருக்கு. நீங்க ஆடியோ கேக்குதா பாருங்க. பேசுங்க. ஆடியோ வரல. இல்ல சார். நான் திரும்ப
Audio? Yes.
இட்ஸ் கம்ஃபர்டபிள் சார்.
Yes, sir.
அதே மாதிரி ஸ்லைட் ஷோ கூட பார்த்துடலாமா சார்? ஜஸ்ட் மொமெண்ட். Yes, sir. It is comfortable, sir.
Yes, sir.
Slide down. Yes, sir. It's comfortable, Senthil Velan, sir.
Okay.
We'll wait for a couple of minutes. I think around 5 minutes we will start, sir. People are joining. Senthil Velan, sir.
Okay.
Yes, sir. Slide show is also working, sir. Can we hear your audibility, sir, again? Can you speak, sir?
Yes, sir. Are you able to hear?
Yeah, it's fine.
Yes,
Yes,
sir.
sir.
Audible, sir.
Audible.
Okay.
Mohan Das, is it comfortable? Professor Mohan Das?
Yes, sir. I am very comfortable. I am audible to everyone, sir.
Yeah, kind of. Yeah. Professor Gopinath? Yes, sir.
Yes, sir. Yes, sir. I'm also comfortable, sir.
Yeah.
I'm keep on admitting the people who are coming.
Yes, sir. Kind of you, sir.
At present, 33 members are there, so
Yeah,
I'll
yeah.
keep on.
Yeah,
Okay.
please, sir. It is right time to receive people. Yeah.
We'll wait for 5 more minutes, sir.
Yes, sir. Yes, sir. We will wait for 5 more minutes. Yes, sir. Professor Gopinath, sir. Hello. Professor
Yes, sir.
Gopinath, sir. Shall I request Senthil Valan, sir, to sir, shall I start the session, sir? I will welcome.
Yes, sir. Yes, sir.
I'll start it, sir.
Yes, sir.
Senthil Valan, sir, shall I, sir, comfortable? Yeah, yes, sir.
Yes, you can start.
Good evening, all of you. I request all the participants to mute their video and audio. On behalf of Department of Mechanical Engineering, Sri Venkateswara College of Engineering, Sri Perumbudur, I welcome today's resource person, Dr. Senthil Valan, Professor, Department of Mechanical Engineering, Indian Institute of Technology, Guwahati. We are very happy to receive you, sir. We will be delivering technical talk on design challenges in thermoplastic composite mission elements. We are very eagerly waiting to hear your valuable talk, sir. Now, I invite Dr. Mohan Das, Associate Professor, Department of Mechanical Engineering, SVCE, to invite today's session speaker.
Thank you, sir. Thank you. It's my pleasure to extend a cheerful welcome to you all for this second day of this 5-day FDP. And it's a great honor for me to introduce one of the key speakers of this 5-day FDP, Dr. Senthil Valan, sir. Dr. Senthil Valan, sir, is being associated with IIT Guwahati since 2006, and currently is working as a professor in the Department of Mechanical Engineering, and also is Associate Dean of Academics for postgraduates. And he also worked as a Vice Chairman and Chairman for IIT JEE examinations in the year 2012 and 2013 respectively. And his research area includes fatigue and tribology of polymer composites. And he has published more than 50 peer-reviewed research articles in high-impact journals. And 5 research scholars have completed PhD degree under his mentorship. And in recent years, he has begun to explore engineering aspects in the Siddha medicine domain. And today, he is going to deliver the lecture on design challenges in thermoplastic composites machine elements. So with this brief introduction, let me hand over the session to Dr. Senthil Valan, sir. Thank you once again.
So, good evening to all. Thank you, Dr. Mohandas. Thank you, Professor Ramesh, for giving this opportunity to interact with the people. I'm thankful to them for giving this opportunity, and also I invite all these people who are showing keen interest, even during this challenge time. People are showing interest to update their domain knowledge. I'm very happy to share whatever my experience during this period. If you look at the topic, though we have written as a challenge, right now you must have understood we are facing so many challenges, but also people are looking this as opportunities. So it is not really a challenge, rather it is an opportunity for the people like us to contribute to this domain. Though initially it looks like no challenges or problems, but we have to really look at it as an opportunity. Being a thermoplastic composite, if you look at that, what exactly thermoplastic composite, most of you are familiar, because I hope most of you are from mechanical engineering domain. You must be familiar with composites and so on. And I'm not going to repeat what is this composite and so why composite we are preferring and so on. Only thing is, somebody may not be familiar with this thermoplastic composite. So I thought, okay, I'll just give a brief introduction about this thermoplastic composite. So it is basically a discontinuous short fiber composites. When we say discontinuous, it is not like a continuous fiber where thermoset is being used, where no people bothered about ply, lamina theorem and so on. So as far as the manufacturing is concerned, it is almost similar. You don't require a special technique, like whatever process people use for thermoplastic. You can use a similar topic or similar arrangement for the thermoplastic composite also. say injection molding, extrusion, compression molding are some of the commonly used manufacturing technique. So those similar techniques can be extended for these no thermoplastic composites also. Since fibers are discontinuous, we have to take care little about this some nozzle design and no some fine tuning of process parameters, but not major changes will be there except fine tuning the process parameters and all. When I say discontinuous, what would be the typical range? It is in the range of mm. If you look at that, typically in the range of, you know, in the case of long fiber thing, because again in the discontinuous, again we have two class called long fiber and short fiber. Though it is discontinuous fiber, discontinuous short fiber in general, but the same thing can be done through the pultrusion and process, and then it will be little longer, and the fibers are known aligned in that. Whereas if it is little smaller, it will be randomly oriented. So you can see that no, what is that random orientation within the fiber, and what is that aligned orientation within the pellet. Pellet means it is a single a small particle of the raw material. It is not a part; it is a raw material. Pellet you must have seen similar no to our in the shape of rice, sort of that much smaller. So we have two different class. One is within that pellet you have well aligned thing. So this type of raw material is being processed through pultrusion, whereas this type of no discontinuous no random one is done by extrusion. Extrusion pultrusion is nothing but no one is pushing and other is pulling out. The extrusion is by pushing out, and this is like a pulling out and all. We have slight difference, and we will be discussing this no effect when we discuss about no in more details. So how why exactly people are preferring is because of the no less weight to strength ratio. The composite, that is a major advantage. We are all very much familiar with that. And naturally, you know, when we go for a composite, it is nothing but no to have a better mechanical strength. In the specifically as far as a mechanical engineer is concerned, we will bothered about the fatigue performance, which is basically, you know, the periodic cyclic type of load. No, it should behave in a better way. And the other one is a tribological one, which is nothing but under no the contact condition. Physically, when no the materials are being in contact, there will be a wear and tear no issues. So the friction wear performance is nothing but your tribological performance. And some damping characteristics. Most of the time, no, this polymer class of material is being considered for this damping class of material, damping purpose. It is to observe the shocks and vibration, noise related thing. So and also the damage tolerance, because we are familiar with this fracture mechanics. Like if it is a brittle material, like, you know, even if there is a possibility, if there is a small chance of crack, then it will grow faster and so on. So the material should absorb and it should not grow, the crack should not grow. So people are preferring this damage tolerance also. So with this background, no, we will move on to this no the today's topics. This presentation basically I have arranged in this particular fashion. Uh, though in the initially I said challenges in thermoplastic composite, specifically I am addressing only the thermoplastic composite. Even if you look at that, only thermoplastic, that itself can take another 2-3 lectures. So thermoplastics, like being a viscoelastic, that itself is a challenge that itself is to be addressed by the manufacturing and design engineers. But rather, in this thing we are covering the composite, thermoplastic composite. It is not only simple polymer related issues, but when you add some reinforcement with this polymer related, what are all the other issues which will come up and how this can be addressed and so on. So it is not just polymer issues, but polymer composite, the two thermoplastic composite. So the first, if you look at the first topic, it is the directional shrinkage in the injection molded thermoplastic composite gear and its effect on gear metrology. We'll quickly go through in detail. We will in detail anyway, we will see in the slide wise and all. And then no reinforced fiber length and diameter of the composite and its effects, micromechanical behavior, the effect of fiber length on the material damping, not sensitivity, of the and particularly the material. Then the leaf spring. So in this presentation, I have just covered two things. One is the gear, and other is a leaf spring, which are basically, if you remember, our major issues or major challenges lies with these two components, where the type of loading coming into this type of elements are very complex, and because of the geometry and shape and all, then the designers have more challenges when you solve this type of gears or leaf spring thing. So we have just touched upon these two mission elements. And issues like, whenever there is a discontinuity, because any material, any machine element, we cannot have without any discontinuity. You may require to make joints, where you may require to make a hole. So then how exactly this will particularly behavior? So that is about the knot sensitivity. So when there is a hole, how it will behave, and so on. So these are some of the things when we will discuss in detail. You will understand more thing. The first part is the directional shrinkage in the gear. If you look at this is a mold, one type of mold. This is called three pinpointed gates. These are, we have different types of gates. These are pinpointed gate, and this is a cavity. This is a three plate mold system. This is a molded gear. If you look at that, we have different types of gates, but say for example, let us arrive this particular configuration or the design of the gate. Then what are all the issues if you come into this? So basically, this gate location design can be done through some analytical or numerical technique, and this was done with a tool, a mold flow simulation software, a numerical technique. And then so that the whole idea is so that you will able to identify the best location. What is the purpose? The purpose is basically, the pressure and temperature throughout the product should be similar. If you just remember that, we are talking about a temperature sensitive material, where it is basically more on sensitive to the pressure and temperature. That means, if you maintain a different pressure at a different location, you will end up in getting a different shrinkage. That means the part size will be different at a different location. So we wanted to have a uniform pressure and uniform temperature throughout. Say even I don't want to have a different temperature here and here. So naturally, when the temperature difference between this part and this gear, or this tooth and this tooth, you have some differences that is going to contribute to your dimensional change, and finally your functional characteristics. No, in the sense, we will discuss about more about the gear metrology. It is not like the normal part, where you simply bothered about two dimension, lateral dimension and linear dimension and all. We have a lot of metrological issues. So this is the challenge. So how exactly it can be done? If you look into this, um, this is a mold flow simulation. So even if you make use of the simulation software, then you will able to see that three different location, and then you are just pouring the molten material, and then that is going to meet each other. This flow is going to meet each other, and naturally you will end up in having a different shrinkage and so on. So this is what we mean to say the directional shrinkage. When I say directional, that means the fibers will orient in a particular fashion, and fiber orientation and along and across will have a very different behavior. So we will anyway cover up those issues. Uh, so what exactly it is going to contribute? As we said, the part thickness and geometry is getting affected by this melt flow. Viscosity, because we know that this is a viscous class of material. It is not like your elastic material, so it's a viscoelastic. And the heat transfer characteristics also, because depends on the temperature you are maintaining and pressure you are maintaining, that amount of heat you are able to generate or dissipate, will be different at a different part. So finally you will end up in getting a differential shrinkage. So what is the challenge? This is about simple polymer, but when you add the fibers, reinforced fiber, you will able to see that you can see this difference. This is unreinforced material. This is the reinforced material. This is a simulation anyway, though I will be showing the actual shrinkage value also. You can see that broadly it reduces the shrinkage because what we have added is a glass which is not going to behave like a polymer. These are basically elastic material, so you will not have shrinkage unlike your base matrix and all. So naturally you will have a reduced shrinkage. So you can simply see the value here, 7.8 or 813. Here it is 6 to 12 and so on. There is some drop in shrinkage. Not only that, it is not just dropping the shrinkage. That means no, you have to just keep the part cavity accordingly to compensate. But issue is not end with that. If you look at that, the orientations, the fibers are discontinuous. So they are going to orient along the mill flow direction. And again, it is simulation. I'm going to show the actual picture also towards the end. If you look at that, the fibers are, it's radially, if you look into this, the glass fiber reduces shrinkage and fibers are oriented along the melt direction. Okay, the melt direction means this is your point of gate. It is just flowing outward. If you look at that, then it is aligned with the ends of the profile. And so that means if you measure this the outside diameter or the hub diameter, and all you measure in this particular phase with direction, which is nothing but you are measuring in one along the fiber orientation and you are measuring normal to that. Okay, so naturally you will able to understand that when you measure in this particular fashion, and if you measure in this particular variation, so you will have a big difference as far as the shrinkage is concerned. Because if you look at that, the amount of no material available over here, within that the amount of fiber presence here, whereas in this direction. So this is really going to make the huge difference. And this picture will give an idea about the two different thing, like particularly the the tip circle or hub diameter. So this is your hub portion, this is your tip circle diameter, where the fibers orientations are coinciding, whereas normal to the fiber orientation is nothing but your phase with direction. In addition, the bore diameter pin is going to prevent the shrinkage. This is internal core like material. So typically if you look into this, you will see that this is the actual measurement. That was a predicted one. This is the actual measurement. The actual measurement, if you look at that, the hub diameter, say for example this hub diameter and face width, you will able to see the difference. So this is for a one class of material like unreinforced material. The deviation, you can see deviation is very large over here, whereas the the face width deviation is very very less. But when you add the fiber, exactly same behavior but slightly lower. The deviation from the actual measurement, it is slightly over, slightly reduced because of the presence of the fiber and all. So even this is without the fiber, the polymer molecule orientation, this is not about the reinforced fiber, the polymer molecules are getting oriented, and that is getting affecting of our geometry across different part. But we know that the hub face with these are not very crucial, rather we will be concentrating more on the gear tooth profile. That also we will be looking into the following slide. So in this slide, if you look into this, what exactly it is, the packing pressure contributes less face width. Why the face width is very less? Because you have a packing pressure is going to contribute larger in that particular direction. And then because you are packing in that particular normal to that direction, but whereas you don't pack it along the circle, which is the tip circle, the packing is normal to the face width. That means you are holding your three parts or plates are going to hold with each other, and the orientation radial to the tip circle restrict the shrinkage and hence a less deviation. Orientation concentric to the hub diameter does not restrict shrinkage and hence large deviation, and pin restricts the internal shrinkage and so on. So even different location itself, you are end up in hitting a different uh, dimensional shrinkage. And more than that, if you look into this, this is um, these two is also given idea about the deflection, which is variation in shrinkage. The deflection is nothing but the variation in shrinkage. If the shrinkage is not uniform, then it is, you are going to end up in the called deflection. This is not the deflection due to the operation and so on. Okay, and this is due to difference in shrinkage. So that is also going to contribute. This called warpage. This is called warpage. So this will just try to bend with each other. This is not only due to the minimum thickness and issues. The warpage, we are all familiar with this warpage in the casting one. It is similar to that, but as far as the injection molding is concerned, this is more related to the direction. This is more related to the shrinkage deviation. When the shrinkage is not uniform, and this is going to contribute. But how exactly this is going to affect my gear? This is going to induce more tooth to spacing error. There are teeth and there are spacing in between. Now this deflection is going to contribute more spacing error. Okay, that is why if you look into this, so this is unreinforcement and this is a glass reinforced one. This is a simulation again, and you can see that that is also, you can see the red, more red over here in the case of shrinkage and in the case of unidirectional and all. So this is also another aspects we need to really bother. And this is the actual picture, the actual the flow which we were talking about, meeting of the flow, meeting of the melt and so on. You can see that this is the part where the molten material starts pouring, and this is called fountain flow. From here the melt is flowing, and whereas these two, because these are three pinpointed, and this pinpointed, if you see that the melts are going to meet at this point, this is called well line. So anyway, these well lines are weaker, but this region we are not going to have any critical section, because we are not going to our loads are not going to act in this direction and all. But you can see that what we have simulated and what we have exactly observed is also seen over here. So these well lines you will able to see, the fountain flow you will able to see. Not only that, the fibers orientation, which we said in the earlier, it is getting oriented along the tooth profile, and along the mill flow. Also you will able to see how the fibers are getting oriented, aligned, not exactly, but almost aligned and all. You are able to see that in this region and all. And more than that, what is more important is the final the metrological aspects, and how this orientation is going to really contribute. This is one particular type of thing called, this is called gear tooth profile. And the gear tooth profile itself, there are many thing called pitch deviation profile, form deviation and so on. So here you can see that we took three teeth at three different number of teeth, 1, 6, 12, and we have moved from the base circle to the tip circle. And ideally it should be a straight line. It is, though it is an involute, but the variation what we are trying to observe is basically the variation of the involute form deviation only we are trying to get. Ideally it should be a straight line, but you can see that how exactly it is getting. This is unreinforced one, this is a reinforced one, and you will able to see that the less amount of, in the case of glass reinforced, you will see that there is a less amount of shrinkage, because ideally you expect a straight line. This is achieving here, but the problem is this is the total. You will able to get two different thing. One is called total profile, as well as the form deviation. Form deviation is nothing but you have some mean line, and within the mean line you have some variation. Okay. But here within the mean line you don't have much form deviation. So this, in unreinforced material, the form deviation is not so much, but the total deviation is larger. Okay. So so typically when you design the gear, so it depends on what type of deviation which you can tolerate. Accordingly we must able to see that. And not only that, we have other type of deviation, metrological deviation, which is also to be considered carefully. So these are the total lead deviation. So if you look into this, because the spacing what we have seen is about the spacing. So this is about the lead deviation. So I hope you are familiar with the form, profile and lead. The lead is along the face width direction. Okay, it is not from the base circle to the tip circle. That is what we have seen in the here. It is from the base circle to the tip circle. Whereas if you look into this, this is from along the face with direction, because if the gear tooth has got some 6 mm or 4 mm and all. This is 6 mm gear, so you will able to see that face width. With the width, along the width also you have to measure, because that is also going to play a major role. So that is the lead deviation, that is called lead deviation. If you look into this, you can see that surprisingly, unlike the earlier slide, the unreinforced one is showing a poorer performance when compared to the reinforced one. So the earlier one, no, it was better as far as the profile is concerned, but if you look into the lead is concerned, you can see a variation along the from the top to bottom or left to right and so on. Okay. Earlier we have seen the reason also why in the particular direction of the lead, or why in the particular direction of the no the radial direction, the shrinkages are no different. We have already seen. Again, we don't want to repeat it, but the variation in shrinkage, how it is getting affected in your metrology, you will able to understand how the metrology is getting affected. So it is not just by adding some reinforced you will able to get a better gear. It all depends on which no direction, orientation, the directional shrinkage, and that will in fact deteriorate even the when compared to the unreinforced one. And not only that, the spacing also going to make the difference. Whereas if you look into that unreinforced one, which is in the red color one, when you add the fiber, okay, you will you see that you are disturbing more on the spacing issues. The spacing is going to contribute about the noise generation and so on. It is more related to the pitch spacing, is more related to the noise generation and so on. So though you may get a better high strength gear, but no it may generate more noise and so on. So this is just metrology. We are not even no we are not showing even the test result of these gears. Just a metrology. You just mold, you take the mold, and then you are trying to get the metrological aspects and all. So this is some sort of summary we can arrive. So if you add this type of material, this is going to reduce the shrinkage, but we have to remember this is going to contribute this directional shrinkage. Okay. So that means directional shrinkage is somewhat controllable. So it but we have to be careful in that. And the location of the gate with reference to the gear part influences viscous condition and so on. Alignment of fibers along the profile decreases profile error. Hard fiber at the skin surface increases gate profile and load form error and so on. But on the other hand, the skin surface, that is the form error, is because of that on the surface level, both the lead form and tooth profile is getting affected. So finally, this is what we mean to say the directional shrinkage. You need to have a careful mold design and so on. In the next topic, so we just we have just covered one topic. No, we have to be careful about the directional shrinkage. Now we will discuss more about some no the fatigue and no the friction wear behavior of these gears, these developed gears. So this was a test facility used to develop, to conduct some experiment, and I will not be going in detail. This is just a drive motor, and this is a driven system, a dynamometer like sort of system. And these are some of the sensors which are used to measure the torque, temperature, acceleration, noise, and such thing. We will not go into the detail. If you look into this, these are some fractured surfaces. Again, no, we have used a different class of material, but I am what is required only I am going to just cover up. Broadly, we have used three class of material in this particular topic. I am going to cover up glass reinforced and carbon reinforced. Within the glass reinforced, we have nylon 6 and nylon 6. We have used this for different objective, but finally at the end, we end up in getting a different sort of results. If you look into this, where the fractured surface, there is not much fiber is getting separated. Pullouts are not much happening, though you are able to see some fiber extruded and all. Not much pullout, not much hole you are able to see. Sufficiently, the fiber and matrix are in bond with each other. Good adhesion. This is separated fiber. Good adhesion is happening. So naturally, you will able to see a better, the wear performance, resistance, and so on. But typical worn out surface also, you will see that how the wear marks are observed. from the pitch surface and so on. What is surprising, if you look into this, to compare the wear particles between the glass reinforced and unreinforced material, you can see a big difference between the glass reinforced and these two are the unreinforced material. So at higher loads, basically at higher contact stress, because we are all familiar with the the Hessian stress and contact stress related, particularly the gear is subjected to both bending and contact stress. So we have to bother about both bending strength and contact strength. So naturally, you want to prevent the wear resistance, or no, you wanted to have a better tribological property. You need to work on more on contacting. If you are really bothered about the bending thing, you have to bother about the root stress and so on. So this is about contact stress related, where if you will able to see that there is a fine particle due to the normal run in wear, but when you cross that, basically the critical the contact stress, you will end up in getting a fibrous wear particle. In both the case, you will able to see that the it's a fibrous sort of thing. This is like your run in wear. So this is not, this is acceptable, this is not going to make no any issues. So you have to decide our critical load so that you avoid this particular class of thing. And surprisingly, you will able to see no big difference between these two also, unreinforced and glass reinforced material. And regarding the bending aspects, again there were a lot of other work done, like the effect of speed. We normally see that no, in the case of metal gear, the speed is not going to make any difference. We never bothered about no what is the no effect of speed and all, except the PV criteria. We don't really give much importance. But the gear, no, being a viscoelastic material, we need to work more on that. I have not covered this particular aspect. Like, sir, I am just giving one small no fact before move on further. Normally, we expect no, when you run it at higher speed, no, the wear will be more, but it will happen opposite. In the case of polymer class of material, it will happen in opposite. That means if you run it at higher speed, it will perform better, because the the contact time will be relatively less. And when the contact time, the rate at which you move or slide, is faster, the material will behave in a better way, because its strain related issues are also there, and contact time, these two contributes and all. So when you look into the bending behavior, as we said, no, both bending and contact, this is about bending one. As expected, no, the fibers will act as a bridge between this cracked fibers, and also whether it is unreinforced or no glass reinforced or carbon reinforced, you will always see that this is going to restrict our this is going to restrict our crack growth and so on. So it is always going to be helpful. There is not much no issues over there. But what is surprise no element was, we were thinking that no, by having a carbon reinforced material, because we know that no, carbon is a better better material, superior material than glass one. So you expect a better fatigue strength. This is what we expect. But what is surprisingly, in fact, we had a poor or inferior no behavior. So it is not just the base thing. What is more important no is about the size. So the smaller diameter means, again, these are in microns. If you look into this, the average length is in the 175 200 micron, and diameter, if you look into this, it is in the range of 10 micron. Okay, so very small deviation, you don't find much difference between this and this. But you will see that a very small, because that is why this is called critical fiber diameter, critical fiber length. These are very crucial. So though carbon is expected no is to be no superior material, but you will see that no, because of this reduced surface area, okay, and then no, your adhesion is seriously getting affected. And what is really issue is, so if you want to maintain the same volume fraction or weight fraction, you have to put more fiber. Okay, so because it's smaller diameter, so when you have the more fiber, you will have more fiber ends. So the length, the diameter is going to make the no more fiber end. So that is also a very weaker chance. When the fiber end is a really a crucial issue, when you have more fiber end, it is going to contribute no a serious effect, particularly the tribological or the matrix adhesion issues. So this is what is finally reflected. If you look into this, this is about another class of material. where we have used a 6-6 material. Again, we expected no 6-6 material will be better than 6 material, because this is a different polymerization. It is expected a 6-6 material will be, nylon 6-6 will be always better than nylon 6 material. But surprisingly, when we add when we make use of a different glass material, so that is really, you can see that more pull out. You can see a large amount of holes over here. So it is not because of no 6-6 and all. In fact, 6-6 is better than 6 material, because this one has got a reduced fiber length. So that is going to contribute no, because of this no issues. And carbon, this is about carbon. You can see that huge pull out. You can see a large amount of no black holes and so on. You can also see that pull outs over here. So typically, not only that, the surface energy of a typical glass fiber, though it was not measured, but typical surface energy, the surface energy is the one which decides, the wetting capability and all, how far you are able to join this material with another matrix and so on. Though individually it is better class of material, but unless you take care about to improve the surface energy and the issues about diameter and length, you will end up in getting a poor material. In fact, that is what it happened. In fact, it showed a very poor performance. So if you look at that, this also gives an idea about that how the wear particles, you must have seen the debris particle in the earlier slides, 6 material, whereas the 6-6 material, you can see that the debris are larger in size, carbon, both in carbon and the 6-6 material, glass reinforced material. Even at lower low load contact condition, you can see that the wear particle, debris particle. That means you have to even limit your contact load little earlier than that and all. So yes, it was showing the carbon reinforced gears were having a better bending static strength. Though I have not presented that slide, but as far as the contact condition is concerned, it is was showing a no bad one. It was showing no crack. It take more time to develop, to form, and to grow. That is sure. But it is a contact part. If you look into this, the surface is getting worn out very quickly and so on. This is the summary where we wanted to present over here. So the tribology and fatigue one, it is not just by adding some reinforced material you will end up in getting a better product and so on. It is not so. We have to be more and more careful, particularly if it is a tribology application. Then we have to bother about that surface energy, the fiber diameter, fiber length, and number of ends. Everything is matter. So this is what we have to be careful in choosing the appropriate material for our application and so on. And this another few slides again, I will be touching the same point, but with some other supports. We have done some analytical and numerical to understand the effect of this fiber ends and fiber surface and so on. So typically typically a unit cell was modeled, and then we tried to see what is this micromechanical model is getting affected between about the stress transfer between those things and all. Um, so this is not in the part. This is just some numerical work we have done to prove that at various volume fraction with the different length and diameter. We have seen that to maintaining at different ratios and all. We were trying to understand what is this critical fiber and what is this critical fiber length and so on. So that was our objective. If you look into this, different conditions were taken, and then we were trying to understand how what is this interface is going to affect and so on. So there you can see that the end, the fiber end, you can see that huge the transfer of load is happening over there, whether it is a tensile load or a bending load or whatever type of load. If you look into this, so finally you have to really bother about this critical length. Okay. Beyond a particular critical length, it is not going to make any difference. So but you have to choose your appropriate material, so that you have to make use of material where, so that a critical length and critical diameter is considered. For that purpose only we have kept this slide. And not only that, the radius, the fiber fillet radius, that is also going to make a huge difference. So how this can be done? whether people manufacture, no, not like a single material and people add the material, but this is done through, like as we in the very first slide I said, extrusion, pultrusion and all. That is going to decide the type of end you have. So always as expected, no, always the sharp edges are not at all preferable. So analytically or numerically also you can just prove that, no, how this is going to affect our, no, the ends and so on. So this was the slide where, no, we have identified how this interface is very crucial for us and all. So when we wanted to really design some elements, it can be a gear or it can be any class of material, we have to give more importance to the, you know, the type of fiber. It is not just a glass or carbon or Kevlar. We have to give more importance to the even the size of the fiber, and then the aspect ratio, the fiber ends. If you have, as we said, no, if the fiber length is shorter, means you will have more fiber ends. Even I think we have some slide, you will understand how that is going to affect our the other performance as well as. So with this, we move on to the other topic, which is the damping aspects. Many of these machine elements, basically we wanted to have a noiseless operation, quite noiseless operation, that is decided by this damping property. So it should absorb this noise, shocks and vibration, everything and all. So this is a typical, a standard technique called dynamic mechanical analysis, specifically mean for this viscous class of material, where you have this viscoelastic issues and all. So this is done based on, the standard testing and all. So it is unlike our normal class of elastic modulus, we will bother about the storage modulus and, loss modulus, and then the damping ratio and all. So basically we expect that higher the damping factor, damping ratio means, no, the material is no good for your damping application, like in the gear and leaf spring and all. No, people expect that it should absorb the shocks and vibration. So though you add the glass and carbon for your fatigue and tribological aspects, but at the cost of your damping. So it's a very obvious, when you add the elastic material, the damping property, that is the ability to absorb the shocks and vibration, noise is getting disturbed. If you look into this is unreinforced one, this is glass reinforced, the carbon, which is even stiffer material, no, it is still lower. So this damping factor is the one which gives an idea about how good is for the damping application. Higher the damping, better is the material for your application. So this is done at various frequency, various temperature and so on. Not only that, that is a material, but this is about the actual noise generation during testing. The one slide which we have shown, when you run it at different time duration, different load, this is for a particular load 1.52 Newton and so on. You can see that these materials, these reinforced materials, slightly generate more noise, because this is you are adding some reinforced material. So because of this, you are disturbing your viscous component, the elastic component is slightly increased. So noise is getting more. Noise is getting more not just by the material. Will also come up with the metrological aspects also. The tooth spacing error we discussed in the slide, that is also getting altered, or that is also getting deteriorated. That will also create more noise and so on. So this is a noise generation. To understand more about hysteresis, we are all familiar with the material hysteresis. That means you will do this loading and unloading and then try to see whether my material is following the same path. If it is taking a different path, then you will say this is no hysteresis. Some amount of energy is getting lost through that. So so some test rig was developed in house, and then we try to see under the gear how it is getting hysteresis is getting done. And also we again know the class of material we have used, we try to get the hysteresis. This is a loading and unloading curve. You can see that unreinforced one is obviously have the more hysteresis, whereas the glass and carbon one it have got the less hysteresis. This will also indirectly gives about the amount of heat generation due to the material hysteresis, because you are subjecting this material to the fatigue load, cyclic load. So because of the cyclic load, you will end up in getting the heat generation. And naturally, when there is a internal heat generation, this heat generation is because of the molecular collision, particularly this polymer molecule and then polymer with fiber material and all, they will collide with each other. that will generate internal heat. And naturally, being a polymer, heat sensitive material, this is going to soften the material, weaken mechanically, and so on. So we have to concentrate on about to maintaining this hysteresis also under well controlled conditions. So for that purpose, we have done this particular exercise. So if you look into this, so these are the measured surface temperature. This is the deflection. This is the measured surface temperature. Again, we made use of some non-contact techniques with IR camera. We measured the surface temperature of the gear. It is not the exact temperature, but the relative temperature. So the relative temperature, if you see that, naturally the unreinforced one showing higher temperature, because the dissipation, the heat generation is also more, as we saw that just now saw that hysteresis loop larger in size. When you add the fiber, naturally this loop size is smaller and smaller. You will able to see that so in that way, the heat generation, the internal heat generation will not generate more when you add the fiber. In that particular aspect, this is better. um, and other aspect is the metrology, because particularly the noise is because not only because of the the material aspect, but also the geometrical aspects. The error, the worst pitch error, which is the contributing for the noise, is basically worst means like between 1 and 2, with 1 and 3, 1 and 4. There are cumulative pitch error. Again, you identify the worst pitch error out of this. What is the worst pitch error? There, if you look at that, the reinforced one have a higher error when compared to the unreinforced one. So it is not only the material aspect, but also geometrically also it is poorer. And because of that, you will end up in getting a larger dynamic load and so on. These are theoretically calculated, these are not exactly measured, but these are measured one. The which pitch error and all is basically measured one. So these are measured one, whereas these were theoretically computed and so on. So in the damping, we wanted to give some sort of summary out of that. When you add the reinforcement, naturally it will increase the modulus, particularly the storage modulus, thereby damping factor is reducing. And damping factor reduces and gear accuracy induces more noise generation, and addition of reinforcement decreases the amount of hysteresis and hence in its surface temperature. So damping characteristics influence the gear performance. So any machine element, it is subjected to this contact and so on. So the ability to observe the shocks and vibration, noise and all is also very much crucial. In a way, we were all thinking that okay, when you use a polymer class of material, it will be better. But when you add the fiber, it is getting more complicated. That is what we need to understand from this. Um, and the next topic I wanted to cover is about the damage one, which is the fracture mechanics aspects. Again, we started with some simple specimen level understanding. Then we move on to the part, particularly the leaf spring application and so on. Again, this was a standard specimen, tensile specimen, and we have done and standard diameter holes. And then we did some tensile test under this 3 class of material again. We took 2 class of material. One is a short fiber and other is a long fiber. In the very first slide, I gave example for the short fiber and long fiber. The fibers are getting random within the short fiber, whereas the fibers are well aligned in the case of long fiber and so on. So in those cases, you will able to see that what is really happening to this notched and unnotched one. So we are trying to understand what is this notch sensitivity and all. So what you do, you will perform the tensile and as well as the other basic test with hole and without hole. It is not just getting the the load coming into that, because without the hole means you have to again reduce the diameter in that cross section area, and then trying to get what is happening to the not strengthening effect or not weakening effect and so on. So even we have done some fatigue load also. So you will able to see that the fracture strength, The fracture strength, if you look into this, the under this class of material, which is a long fiber one, you will able to see a drop. Whereas both this unreinforced and the short fiber no material, here we have used a different class of material. It's the polypropylene. In the earlier studies, we have used the polyamide, which is a nylon-based material. So here you can see that no, when the notch diameter is no increased from 2 to 4 to 6 and all, you can see that there is increase. It doesn't mean that your strength is getting increased. As we mentioned, no, the net strength, that means you have to subtract the diameter of the hole, and whatever amount of area available for your resistance only you have to consider. So with that, no, you will able to see that there is a slight increase over there. This is we call it as no strengthening aspects and all. This is your weakening aspects. So this is how we try to basically to understand the knot sensitivity and all. So the net area used to be consider for your strength capability and all by subtracting the knots area and all. So we need to really bother about this knot sensitivity. That means when there is some discontinuity in the hole, discontinuity like a hole in your material, you will able to see that no, it is not always deteriorate. In some time it will help also. When your materials are basically uh, uh, if you look into this, when the materials are sufficiently having some viscous component. Okay, when the material is viscous component is relatively very less, then it is not going to help. If you look into this long fiber reinforced one, this is deteriorating when the larger diameter. But whereas this one, if you look into this is showing improved one. Okay. Not only that, the fatigue aspect, we are all familiar with the knot sensitivity, how to get the no sensitivity, knot sensitivity and all KSKT, we are all familiar with that. So you can clearly see that no, these two are basically dropping. This knot sensitivity no, in these two cases are basically unreinforced and short fiber, no, it is dropping down, whereas this one no is increasing. So in this case we call it as a strengthening effect. Why the strengthening it is happening? Because this material has the ability to undergo the localized yielding. Localized yielding will happen no near the hole and so on, whereas that possibility is not happening in the case of no brittle class of material or high strength class of material and all. So this was done at even the specimen level. You can see that no, near to the hole, near the knots, what is really happening to the fibers. Okay, you can see that the fiber bending no issues, the notching issues. So now we wanted to understand how this is getting reflected in the the mission element part. Particularly we took a class of a leaf spring. uh, this is again another sort of work where this is a mono leaf spring. uh, we are familiar with the leaf spring, graduated leaf spring, no, many small larger length than master leaf spring, we are all familiar with that. But this is a single one, and you wanted to have a similar performance, in the sense you can see that the middle you have the larger width. Okay, the way in which in our graduated leaf spring also, no, you put a smaller, then increase, keep on increasing, so that no, to have the normalized bending stress, no, you keep the no different length of the fiber uh, leaves and all, so longer, shorter and so on, so that no, at the middle you will able to take a more load, so then to have the normalized bending stress. Same thing is kept over here, so that is why we kept a larger no width here. This is a single leaf spring, but you will able to achieve the similar performance what we have people are achieving in the graduated leaf spring also. So we will not go into the detail of the other aspects, no gating location and so on. Again, we took two different class of material, unreinforced and glass reinforced polypropylene. Issue we will concentrate about the notch aspect. See, finally, these fibers, if you look into this fiber is to be, this leaf spring is to be joined with your no mission, no your structure, like your chassis and such thing. So how are we going to join? Again, by making no the holes, fasteners and all. So in those cases, no, you have to make a hole. So now what is the issue is, when you make the hole, how is it behaving? How, because your leaf spring is not just based on no the joint behavior is also we have to consider. That is why we said how the knot sensitivity, particularly with the reinforced material, how is going to affect. That is why we saw the specimen, the behavior and all. This is how typically people um, um, carried out this joint strength behavior. So again, if you look into this, different diameter of the holes were done, and different types of loads particularly were given, fatigue loads. And then we observed a different types of failure between this and here. Get a different types of failure. You can see different types of failures, the bearing failure, the shear failure, and all those failures under different loading conditions. This is a typical the loop during a fatigue load. You will able to see that my loop is getting enlarged. We have seen in the gear, no simple static load you apply and reduce it. Now this is a cyclic load. In fact, we have used fatigue uniaxial fatigue testing machine. Only we have made a test rig, so that whatever simple tensile load or compressive load is getting transferred to the bending load and so on. And now you are measuring the deflection continuously. So there you were able to see the load deflection behavior. So as the time progresses, you will able to see that because of the whole extension, say this is for after a particular number of cycles, you will able to see my hole is getting enlarged, and you will able to see the enlarged here the loop is getting enlarged.
Sir, comfortable? Sir?
Yes,
Yes, sir.
yes.
Okay, sir.
I think there is some little hanging.
Thanks. Sir, comfortable?
Yes, I'm just opening again.
Okay, okay.
Is this visible?
Yes, sir. Yes, sir. It is visible now.
So this is what we have done for various diameter of the holes. We have and also the clearances, because if you look into this, know what type of clearances you are giving in the microns. If you look into this between the joints, between the pin and the hole, that is also going to make a huge difference in the fatigue behavior and so on. So that was our objectives. We have done how the loop is getting enlarged. Also, we were able to see at the different clearances how that is getting affected. Uh, So this was the slide we were trying to finally achieve it. If you look at that, the knot sensitivity, because of the the different we have considered three class of material, and how the knot sensitivity is getting varied. Also, we were trying to understand from this exercise. And in this particular portion, you will able to see that uh, this is a final bending strength. How between this low cycle and high cycle, we are familiar with this type of low cycle and high cycle thing. Any fatigue, any mission element subjected to fatigue, we have to have a different criteria or different design approach or strategy, because this behavior will be completely different under 10 power 4 and beyond 10 power 4 and all. So the similar thing we were able to see here under low cycle fatigue behavior. Uh, this was this particularly this long fiber reinforced one shows a superior performance in the case of in this high cycle one, whereas in the low cycle the other one was that is unreinforced material and short frame material shows even better performance. Again, no, it all depends on the knot sensitivity and the localized plastic yielding. That was the reason which we have seen it in our specimen level itself. Why this particular behavior also we have seen at the specimen level. Now the same thing we are confirming at the the component level or the mission element level.
Are comfortable?
Yes, sir. Actually, this slide it seems higher some issues about once we cross.
Visible here. Yeah.
So this was a summary. Like we have to really bothered about the fracture strength of this type of material, because it is not that always you will having a continuous material. You will always have some discontinuous. So fracture mechanics aspect is to be really look into that. Particularly, we have just consider only the one particular aspect, the not sensitive. There are many other aspects. Depends on the component and types of load. You will really bothered about different loading condition. Which what we have simply bothered about the knots issues and how that is to be taken care or seen. That is what we wanted to conclude with this. And this slide also will give more insight about about the fiber end issue. If you remember, we said no, it is not just a short fiber is inferior just because of the length. You will have more fiber end. So to prove that, no, again we took specimen level some experimental study. There if you look at that two pictures, you will able to see the this is a short and this is a long. For same amount of volume fraction, no, you will have more fiber ends because this is short fiber and all. So that is going to contribute for the damping as well as the heating issues, the dissipation. That is what we wanted to confirm it. So this will have higher hysteresis area. So again, hysteresis no, we did experimentally, we did this one. When compared to the long fiber one, the short fiber one will have the higher hysteresis because you have more fiber end and so on. Again, this was the one which I mentioned, where we made a specific test rig where simple compression load is going to contribute the bending one. These are some testing conditions and all. So this is a simple load carrying deflection behavior, and these are the loading and unloading behavior, and this is a hysteresis. The one which we have seen earlier was specimen level. This is your the component level, particularly the leaf spring and all. There we were trying to get the hysteresis issues. Again, no, if you look into this, the load relaxation, that means no, you maintain the same amount of thing and then see same amount of displacement and see how much load is required to to maintain that deflection. So you can do the constant load or you can do the constant displacement load in mode in the fatigue one. This was done at constant displacement mode. So this will show the, if you wanted to maintain the constant load, then constant displacement, then the amount of load required will drop down. No, that is called load relaxation behavior. So that also is no indicated over here.
comfortable?
Yes, yes. Taking time for the slide change. During this time, no, if anyone is having any question, can we take, or will once we finish, we'll take?
Yes, sir.
I think
There are
we.
few questions. Yes, Sandil sir. There are some questions we received. I'll ask you the first one. How about the feasibility of fabricating helical gears using this material?
Yes, yes, it is absolutely possible. There is no difference. As we said, no, it is same, similar die, similar process. Only thing is, they must have seen that in the spur gear itself. No, it looks like a simple spur gear, but we have a profile and lead issues, and then tooth spacing and all. So in the case of helical, we have to really bother about the helix no issues are also. So it is possible. Only we have to see that no, it is more complexity is getting no involved. It's possible.
Okay. The other question is, which is the most frequent failure form in polymer gears?
Most frequent failure.
Failure form, failure. They ask like that.
Failure is more the thermomechanical failure only, because unlike no the elastic material, where we don't go up to such a high temperature. Here, no, polymer being a polymer material, the heat generation that we have just now seen the hysteresis, that will also be internal heat generation because of the molecular collision. So when the component is subjected to fatigue load, structural plus this thermal also comes into that. So it is a most thermomechanical behavior. So we have to concentrate more about this thermomechanical no failure aspects.
Okay, sir. One more from Mr. Venkateswaran asked from RIT. How the orientation of the fiber was taken care in the simulation?
No, simulation will do, because simulation always no does about flow. As we said, no, even without fiber, there is a polymer molecules orientation.
Oh,
It all depends on no how the polymer molecule, the geometry, like what is the geometry along the fiber, the molecule will try to orient. How it will be taken care in the sense, uh, I don't know what exactly he means, how this will be taken care in the simulation. The simulation they have considered basically like the way in which shrinkage they have considered. The polymer molecules also is considered. There must be some no appropriate model, flow model, no the fluid model associated with that. So
oh,
they have considered, depends on the viscous model, what is the material you are using. Accordingly, the flow will be simulated.
okay. One more question. Normally, what will be the life of the polymer gears?
No, it all depends on no what is the type of load and no service condition you put. Again, there is no you cannot simply say this material like. But we should remember this. It's typically the elastic material like a steel. If you look into this class of any material you take, its modulus is about 100 times lower. So you have to see that no, definitely you cannot match your material, no metal material. Even if you consider today's material like a peak composite, carbon reinforced peak and all, you cannot replace the metallic material. So it's ruled out. But all depends on no. That is a whole challenge, or that is a whole no issues with that. What is the type of load, or what is the environment you are going to put into this? As we said, no, you have to bother about contact, you have to bother about bending. Then you have to decide, like we shown running where that is safe. But moment when you see the debris particle no coming in a patches of debris of such a thing, that is definitely not no, a good sign. You have to restrict your design load in that lower than that.
Mr. Sterling Prince, he asked, can you tell about a scope of research in fracture mechanics related to this material?
Yes, there is a huge amount of work people are doing on this polymer base, because this polymer itself is a see, this fracture mechanics itself is a very complex problem, and when you use the polymer, it is still going to be a complex. So research point of view, there is a large amount of work is still there is a large amount of scope to work in that. Only aspect is this one. We have to pick up this behavior, this polymer behavior, whether it is experimentally or numerically. Numerically means in the model they have to pick up that particular behavior. They have to have the separate code and such thing. Because even the commercial software like Abacus and all do not have this type of modules along with that. They have standard viscous model. Moment when they add this type of material, the fracture mechanics and all, no, it will be more complex. And similarly, experiment, if they want to do this thing, they have to have such facility to measure the behavior. Say you wanted to measure the temperature, you wanted to measure no high the damping and such thing, no. So the extensometer, sensitivity, all those aspects. Otherwise, there is a huge scope where not much work has been done in this class of material.
Okay. And I think one more. What are all the possible attempts we can give to enhance the fatigue strength? Dr. Vedendran sir asked. How
Fatigue,
fatigue strength? Yes, sir.
yes,
Fatigue
yes.
strength.
Fatigue strength can be, this one method what we are discussing about, the touching only the material aspect. So having some reinforced material, no, this is one aspect. But in this slide, in this lecture, what we are covering is, just by adding the reinforced material, you will not, no, end up in getting the better strength. That is the point we wanted to say. But in general, if they ask, what are all the ways to improve the fatigue? Naturally, we have to see, the what is the it is not just material, the design aspects, uh, in the sense, the geometry, the configuration, the service conditions. Surprisingly, simple with simple service condition also we will able to improve the fatigue strength, particularly the polymer class of material, because this is getting heat generated. If you support, slightly, dissipate the amount of heat by appropriately designing, the appropriate thing, so that the heat generation is getting dissipated easily, then also you will able to improve. Simply by mating a polymer material with a metal gear also you will able to improve, because polymer and polymer mating with polymer and polymer, there is no possibility of no dissipation, because both are non poor conductor, poor thermal conductor. When you mate with a steel class of material, when the heat transfer is happening, you will end up in getting a better performance. So it all depends on, what is the type of components they are looking. There are many ways, material, service condition, the configuration design, and so on.
Fine. I think you can continue your session. Yes, sir.
Fine. So this was the thing, which we were covering up, and then we will move on further, where we wanted to consider about, the damping aspects in this particular thing. We got some experimental results from the forced and free vibration of this class of material, how the response will help us in understanding the damping behavior. So there were some accelerators, some exciters, and we were able to pick up the acceleration, and then we were able to see the decay pattern and getting the response between the lag between this load and displacement. That will also give an idea about how the material is dynamic characteristics of this class of material. So there is always a phase lag between this force and response, particularly the material like the polymer, where the viscous component is there will be always some delay. In fact, though I have not presented this in this particular work, there will be a delay when you mate a polymer with a steel gear, because steel gear is having a elastic material, and polymer one is viscoelastic. So you rotate the steel by a 2 degree means polymer will not rotate by 2 degree. It will rotate only 1.9 degree 30 minutes or something. So this is called rotational delay, and this rotational delay which will cause the operational interference and so on. But what we are talking is a phase lag. That is, there will be a lag between the force and the response. Immediately you will not have the response, so there will be a lag. How that is going to affect is the one which we have listed over here. Then the phase lag is going to give an idea about the rise in temperature, and then the drop which we have said earlier also, under constant deflection mode you will able to see the the long fiber reinforced material is showing a drop, whereas unreinforced that much drop is not showing over here. Similarly, the rise in temperature, you will able to see surprisingly the short reinforced one, which we have also said because of the fiber end. Though the long fiber and short fiber, not much variation, but you will able to see the huge rise in temperature. No, because of the lag and because of the no more fiber ends, you will able to see the temperature and the no drop of the load and all. This is because of the internal friction, no, the hysteresis and so on. I think we are towards the end. So basically, when you design a material for a damping application, particularly leaf spring, no, we wanted to observe the shocks and vibration. The whole functional aspect is basically to observe the shocks and vibration, the strain energy, the and all. We need to really think that by just having some reinforced material, you will end up in getting a better fatigue strength. We should not able to conclude. Because we are basically altering the dynamic mechanical characterization, and that we have to remember those aspects.
Senthil sir,
Yes, yes.
finish now, sir.
Yes, we are towards the end. I think we have only 2 more slides. If there are any more questions, we'll take up. Anyway, the other 2 slides are just a summary of that. We don't have any new findings or facts.
There is one more question from Dr. Santhamarikannan. Will the pressure angle of the polymer gears affects the performance and life of the polymeric gear aspects? Yes.
Yes, yes. Any gear, the pressure angle is very crucial aspect. In the polymer gear is also very crucial. In fact, the pressure angle, what he is talking is about, you will have the operational pressure angle here. This will be slightly different when compared to the, because as we said, the involute are not perfect involute. So naturally, the pressure angle also will not be, ideal. Say you design for 20 degree, but finally you may not have 20 degree. You will have the variation, so it is going to seriously affect. Unlike the like the steel gear, polymer gear also pressure angle is going to play a major role. It will be more, I would say, it is more sensitive.
Oh. Sir, one more. What is meant by the fiber fillet radius? Why this term is important?
Yes, actually, like the way in which you prepare the fiber, this is involved in the manufacturing stage of the raw material. Because as we said, there are 2 processes called extrusion and pultrusion. So it all depends on how you are pulling out or pushing up the fiber. So the end is going to be different. In one is like a broken, the other is having not much broken thing. We have shown it in the analytically, some FEA result also we have shown that fiber sharp edge means it is always, as a mechanical engineer, we know the stress concentration issues and all. It will be more weak. It will be more weaker in that particular region if it is a sharp edge. So we don't want a sharp edge. We want a rounded sort of edge. Like any design, we prefer to have the edges to be, not to be sharp and all. But here, what is important is the interface. The interface will be very weak. Already around fiber and matrix, it will be very weak. And if the end is a very crucial. So if it is a sharp edge, it will be still performing poor.
Fine, sir. And last question from my side regarding the enhancing the damping performance. What are all the recent approaches normally we can treat to enhance such property, because a very high compaction in the running of the gear is required. So what are all the recent research aspects going on there?
I'm not getting the damping aspects.
How to improve in the gear system?
Okay.
Material damping, yes.
Okay. No, there are many aspects. One aspect only we are just covering. No, by having the reinforced material and by using the proper proper coupler, which we have not touched. We have just talked about the fiber and matrix, but there is always a coupler in that coupling agent. What type of coupling agent you are using. But in addition, no, many people are using the appropriate, no, the design changes are also they are doing to improve. Like as far as the gearing system is concerned, people use different material at different region. Even no one I have not presented here. People use a softer material in the no interior portion, and not tougher material or harder material at the exterior surface, so that no, when the contact is happening, they wanted to have a hard surface, but the internal core is basically a soft material. So this is like a duplex sort of material. So there are many aspects, like functionally you can alter the material. You can have the different material at a different regions. Now we have uh, bearing is also, nowadays people are talking about this type of material, this duplex material, having surface one material and the internal some other material. This is mainly to take care about this damping thing. So many approaches, it all depends on who is the person. If some material person means he will work on the material. If design person, they will work on design. Manufacturing person will work on the manufacturing aspect. There are many approaches being are followed. So finally I would like to acknowledge these people. First, my professor, Professor R Nyanamurthy is a professor at IIT Madras. He is my research supervisor. Most of my work is taken from my PhD work, which is about 14 years back. I hope still people are, I am able to present this as an interesting result, because though we have done it 14 years back, but still I could present it, so confidently, where not much I'm just repeating from the text sort of material, or which well proven such thing. And also some of my students, where I have used their work, some BTech work and MTech work, and also one of the PhD scholar. He is my first PhD student, and where he worked it in the composite leaf spring. So I would like to acknowledge them, because it is whatever I have presented, it is because of their support I'm able to arrive this conclusion. And also I'm thankful to Professor Ramesh, who was my actually colleague when I did a PhD at IIT Madras. So I'm thankful to the other his team also for this opportunity to share my experience with other colleagues.
Yes, sir. Thank you very much, Professor Sendilvelan. On behalf of Department of Mechanical Engineering, we extend our hearty thankful because we had a very wonderful and extensive section, and went very interesting way, kind of you. And followed by tomorrow, the title for the webinar section is Aluminum Foams and Behavior and Application by Dr. Srinath Gajapati. He is consultant, Tech Break Consultant India Limited, Chennai. So I request all the participants to join for the session on time. Now the link for the today attendance is posted in the chat box. I kindly request to fill and submit. We wait for a few more minutes online to complete the process. Professor Sandil Balan sir.
Yes. So I hope I can leave, no?
Yes, sir. We can wait, and the process will take few more minutes to complete from participants' end. Yeah.
Okay.
Thank you. Kind of.
Thank you. Thank you.
சார் 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 எனக்கு கேட்கலீங்களே. சார் எனக்கு கேட்கல. நீங்க அன்மியூட்
சார்
பண்ணி.
சார் இப்ப கேக்குதுங்களா?
ஓகே சார். கீழே அங்க லைவ் அங்க கீழே போனீங்கன்னா கடைசியா ரியாக்ஷன் பக்கத்துல யூடியூப் எண்ட் செஷன் போட்டுருங்க சார். எண்ட் யூடியூப் செஷன் இல்லனா என்ன ஹோஸ்டா மாத்தனா நான் எண்ட் யூஸ்.
Yes sir, I will do that then. Fine sir.
சரி சார்.
Sir, it is a Ramesh co-host, no sir. That is one.
ரமேஷ் ராஜா
Ara.
சார். ரமேஷ் ராஜா
Ramesh
கோ-ஹோஸ்ட்னு இருக்குல்ல சார், அதை ஹோஸ்டா மாத்தணும் சார்.
sir, Ramesh Raja. Yes sir. Yes sir.
சார் ஸ்டாப் பண்ணிடுறேன் சார். இப்பதான் வருது ஆப்ஷன், இப்பதான் வருது சார்.